Okay, in 4.1 we were working with the unit circle, which I have drawn here, and we learned that the sine of theta is equal to y, cosine of theta is equal to x, and the tan of theta is equal to y over x, which is sine over cosine, and that works for any angle at all. And within the unit circle, what that allows you to do is get the coordinates of the point where the terminal arm meets the unit circle. Okay? Now, what that is really is just SOHCAHTOA in action in a unit circle. So the sine of theta, we know SOHCAHTOA, sine of theta is equal to the ratio of opposite over hypotenuse. That's still true. In this case, when we draw our reference angle there, we have x and y, and here's our angle. It's true, we have opposite over hypotenuse, but we remember that the hypotenuse is always 1. So when we're doing this, and we have our unit circle, and we have an angle and a triangle drawn here, then the sine ratio, opposite over hypotenuse, is just opposite over 1, which is just opposite, which is just y. Same thing with cos of theta. It's adjacent over hypotenuse. Hypotenuse in the unit circle is always 1, so it's adjacent over 1, which is just adjacent, which is x. So there we have it. Okay? And same with tan. Tan is opposite over adjacent, while opposite is right here, it's just y. And adjacent is right here, it's just x. So the tangent of theta is y over x. Today, we're going to learn that we can actually go in any size circle, any size triangle, and if we have the values of x and y, or x and the hypotenuse, or y and the hypotenuse, and remember we're not going to be in a unit circle, so it won't necessarily be 1, then we can actually use SOHCAHTOA and use the formula for the equation of a circle, which is x squared plus y squared equals r squared, and we can end up generating all of the primary trigonometric ratios even for that triangle. So let's dive into example 1, and actually just before we do that, I'm going to give you a little note here. We need to know which quadrants each primary trigonometric ratio is positive in and negative in. And to do that, you use something called the cast system. So maybe just in your top right, kind of above example 1, you don't need to write this, you already have this, but in the top right, just before example run, we can say primary trig ratios are positive or negative depending on the quadrant that the terminal arm is in. Primary trig ratios are positive or negative depending on the quadrant that the terminal arms are in. So let's explain what that means. We'll draw a little Cartesian plane, and we've got our 4 quadrants. We've got quadrant 1, quadrant 2, quadrant 3, and quadrant 4. And if we're using cast, it's really easy. It's starting in your 4th quadrant, C, A, S, T. And all that helps us to remember is that whenever we're working in quadrant 1, all of the primary trig ratios are positive. Sine of theta will be a positive value, cos of theta will be a positive value, and the tangent of theta will be a positive value because it's a positive over a positive. In quadrant 2, sine is negative. Sine is positive, cosine and tangent are negative. How do we know that? Well, we said that the sine of theta is the value of y, so it's y. Wherever we are on the y-axis, that's going to be the sine of theta when we're working in quadrant 2, and so it's always going to be positive in quadrant 2. So sine is the only one that's positive. Cosine, which represents the x value, will be negative, which makes tan negative because it will be a positive over a negative. Okay? In quadrant 3, tangent is the only one that's positive. You can see that cosine and sine are both negative. Negative over negative is a positive. And then over here in quadrant 4, cosine is the only primary trig ratio that is positive. You can see that because cosine of theta represents the x value in the unit circle, and sine is the y value, so sine is negative, cos is positive, which means tan is negative because it will be a negative over a positive. So if you can remember the cast system for determining which primary trig ratios are positive, let's do this. Where each primary ratio is positive. Okay, if you can remember that, you'll be well on your way as we move along. All right, in example 1, we are given that, so we're going to find primary trigonometric ratios, sine, cosine, tangent, for any size triangle in any size circle. Okay, so we're given that the sine of A is 3 over 5. So sine of A is 3 over 5. Well, I know that the sine of A, the sine of any angle, is opposite over hypotenuse. Okay? So what I'm going to first go ahead and do is draw this triangle so that we can see what it looks like. We know that we're going to be drawing a triangle on our coordinate plane here. And it also tells us that this terminal arm lies in the first quadrant. So somewhere in here is going to be our triangle that we're going to draw. And now remember, it doesn't have to be a unit circle. It's not necessarily going to be a unit circle. I know for sure it's not because the hypotenuse is 5. Okay? And the opposite is 3. So this is going to be somewhere over here. Might look something like that. Okay? Now if this is my angle A, then what I've done is I've created a hypotenuse, and this is a right angle. Then what we have is opposite of 3 and hypotenuse of 5. Okay, so if they tell you that the sine of A is 3 over 5, what do you know right away? We know the value of y is 3, and the radius of the circle that we could draw here is 5. So now our next step is to determine what the value of the adjacent side is, what our x value is here. Because if we do that, then we have all 3 sides of this right angle triangle, and we can generate all of the primary trigonometric ratios. So let's do that first. So we know that x squared plus y squared equals r squared. We know that y is 3, and we know that r is 5. And now with our basic algebra, we can simplify this. I'm going to skip a step here. 5 squared is 25. 3 squared is 9. So I'm going to subtract 9 from both sides. I'm going to end up with x squared equals 16, which means x equals plus or minus the square root of 16, which is 4. Okay? Now, because we know that this angle lies in the first quadrant, what do we know about x? Is it positive or negative? It's going to be positive. Okay, it's moving in the positive x direction. So we have x equals positive 4. And we can put a little note there, because our angle lies in the first quadrant. Okay, now that we have all three values around our right angle triangle, we can finish part A of example 1, determine the exact values for the cosine of A and the tangent of A. So therefore, cosine of A, which is adjacent over hypotenuse, and here's the angle in question, so we've got adjacent 4, hypotenuse of 5. The cosine of this angle is 4 over 5, and the tangent of angle A is opposite over adjacent, which is 3 over 4. Okay? This step right here, just being able to draw the triangle, draw the angle in the correct quadrant, and finish off the right angle triangle, that's going to come back again and again. We will get good at it. You need to get good at it in order to generate the other primary trigonometric ratios. Let's move along to B. B says, determine the primary trigonometric ratios for another angle that's between 0 and 360 that has the same sine value as the angle A that we are working with. Okay, so what it's saying is we need to develop another angle somewhere in one rotation. So it's not going to be the exact same angle. We can't just add A plus 360 or A minus 360. Okay, it has to be between 0 and 360. So one revolution of this coordinate plane around the origin. But it's going to have the same sine value. Well, the sine value here is 3. So realistically, we can just draw this guy across. We know that the sine value is going to be 3. So the y value is still going to be positive 3. It's going to be in quadrant 2, that means. And the other thing that we know is sine was 3 over 5. So that tells us that our hypotenuse is going to be 5. So if we know the height is 3, and we know the hypotenuse is 5, then we know it's going to look like that. And the only thing that's changed here is that the x value here, the adjacent side, has changed from being positive 4 to negative 4. It's the only thing that's changed. Okay, so the sine ratio is positive in the first quadrant and the second quadrant. That's because the x value is, the y value is still 3, and the hypotenuse is always positive. Okay? The point that defines an angle with the same sine then is right here at negative 4, 3. Just like this was at positive 4, 3. Okay, so we have our new angle, and remember our angle is going to extend from the initial arm all the way over to our positive arm. We'll call that angle B. That is the only other angle within 360 degrees that has the same sine as our purple angle A here. Okay? And now we can generate the primary trigonometric ratios for angle B. Okay? So sine of B, well, we knew that had to be the same as the sine of A, but we can still write that it's going to be y over r, right? It's opposite over hypotenuse, which is going to be opposite over hypotenuse, 3 over 5. The cosine of B is adjacent over hypotenuse, or x over r. That's going to be negative 4 over 5. And the tangent of B is going to be y over x, or opposite over adjacent, which is going to be negative 3/4. So you can see what happened if you're paying attention to the cast system here. The only one of our primary trigonometric ratios that was still positive in quadrant 2 is sine. All right, C. C says draw a diagram showing the locations of the two angles and determine how those angles are related. So we kind of already drew that diagram up here. If you haven't done that, or if yours is really cluttered, we'll go ahead and we'll draw another little something down here. But basically what we have now is we have a circle. Okay, we have an origin. We have, and I'll try to use the same colors, we have angle A stretching out up here with coordinate at 4, 3. And we had angle B out here, and its coordinate, where it meets the edge of the circle here, was negative 4, 3, angle B. And what we want to figure out is, how are these guys related to each other? Can I develop some kind of formula, some kind of relationship, so that I can say, oh, in order to get angle B, you just have to do this using angle A. And you can. Hopefully you can see here that as far as A is here, angle B ends up being 180 minus angle A. So, let's say from the diagram, angle B equals 180 minus angle A. And that's true because you can see angle A is 4 units out, 3 units up. So it's rotated counterclockwise enough to get this point 3 units up off of the x-axis. And the same thing has happened here. We are, you don't need to draw this, but boom, boom. We are 3 units up off the x-axis here, which means that this angle and this angle must be identical, okay? Which means they're both A. So B is 180 minus A. D asks us to use a calculator to help you find these two angles to the nearest degree. That's pretty straightforward. We'll show the steps. You're familiar with this, but if we know that the sine of A is 3/5, then we can easily find this first angle by just taking the inverse sine of both sides. So the measure of angle A is the inverse sine of 3/5, and your calculator will punch out a decimal answer, which we'll round to 37 degrees. You need to make sure that your calculator is set to degree mode, so you should be able to see a little D somewhere in there. If not, then you need to go to your settings and change it to degree mode, or just flip your calculator over and hit the reset button with a pen, and then you should be able to, it should automatically go back into degree mode. But if we know that the first angle that we found is 37 degrees and we're dealing in sine, then we know that angle B, the second angle, is 180 degrees minus 37 degrees, which is 143 degrees. So there are the two angles that have, within 0 to 360 degrees, that have a sine ratio of 3/5. 37 degrees, which is in the first quadrant, and 143 degrees, which is in the second quadrant. All right, example number 2 has us dealing with the exact same angle that we were looking at in example number 1, but this time we need to develop find a way to find the other angle within 0 to 360 that has the same cosine as our original angle. Okay, so the cosine of our original angle was, remember, cosine SOHCAHTOA is adjacent over hypotenuse, so we're looking at 4 over 5. And cosine, if we're looking at our cast system, I can just quick draw that off to the side. Cosine is positive again. It's positive here in quadrant 1 with this angle, but it's positive again in quadrant 4. So the angle that we are looking for is in quadrant 4. And remember, our x and y values are not going to change except that they can be opposites. So over here, our x value turns to negative. Over here, x and y are both negative, and over here, x is positive and y is negative. But the 4 and the 3 will always stay the same. So we're looking for an angle in quadrant 4, and we know that the x value is still going to be 4, and that's good because cosine is x over r. So it will be the same here. If x is 4, r is going to be 5 again because the radius is always a positive value and it's always the same. But our y coordinate down here is negative 3. Okay, so we have found the position of our new angle as it rotates around this circle with radius 5. And so what's the relationship here between angle A, let's call it angle A again, and this new angle that we've drawn, which we'll call angle B? What's the relationship? Well, the same distance that we went here for angle A, we're going backwards for angle B. Now, what does that mean? Well, angle B has to start at the initial arm and go all the way around to here, but angle B, the measurement of angle B, is 360 degrees then, minus the measure of angle A. Well, we already found out that the measure of angle A is 37 degrees, and you could do that in your calculator if you wanted to. You could take the inverse cosine of 4 over 5 or the inverse cosine of 0.8, and you would get 37 degrees. Which means angle B is 323 degrees. Okay? Now B says determine another angle between 0 and 360 that has the same tangent as angle A in example 1. So again, we're dealing with the same angle, but now we're looking for the tangent being the same, which means we're going to head into quadrant 3, and it's going to look like that with coordinate of -4, -3. So you can just, maybe you can work across, right? If this is work for A, and this is the work for B. So we are looking for an angle, and I've already drawn it, but we're looking for that angle, and we can call it theta. I suppose we haven't used theta yet. So we are looking for the tangent of theta such that theta is 3 over 4. Okay? Now the reason that this works out down here is because, yeah, it's going to be -3 over -4, but negative over a negative is positive. So we have the same value. So again, and what did we do here? Well, we took angle A, and you can see we just added 180 degrees. Or you could say we went to 180 degrees, and then we went A more, right? Because we're 3 away vertically from the x-axis. Here we're 3 away vertically from the x-axis. Here we are 4 out on the x-axis, and here we're 4 out into the negatives on the x-axis. So all we did was 180 plus angle A. So the angle theta is equal to 180 degrees plus the measure of angle A. We know that the measure of angle A was 37 degrees. So that gives us the measure of angle theta being 217 degrees. Now, at some point you're going to be expected to have these guys memorized, how to find the second angle within 0 to 360 degrees for each primary trig ratio. And here's how it works. Basically, if you're working with the sine of theta, you have found one of the angles. To find the second angle, you simply take 180 degrees and you subtract the first angle that you found, okay? I should write the measure of angle B, that's going to be your second angle, is 180 degrees minus the measure of angle A, okay? When you're working with cosine, and you have the cosine of theta, you've already found angle A, and you need to find a second angle. When working with cosine, it's 360 degrees minus the measure of your first angle. And then for tangent, when you're working with tangent, you've already found angle A, sorry. Then you know that angle B is going to be 180 degrees plus angle A. So go ahead and copy those down, put a box around it, put a big star, and that will help you loads in your homework. Example 3, solving a map problem. So we have the city plan of Port Foghorn uses a Cartesian grid with each grid mark representing a distance of 1 kilometer. So Cartesian grid. I'm going to draw this all in a second. The plan places City Hall at the origin, and Ted's house is at grid point -6, 2.5. And then we have in question A, it's about the angle of rotation to Suzette's house having the same tangent ratio as the ratio of Ted's house. Okay, so basically what we have here is we have a circle on a Cartesian grid. We have City Hall at the origin, and we have Ted's house at the point -6, 2.5. So that probably looks something like that. T for Ted, and -6, 2.5. Okay? Now we're told that Suzette's house has the same tangent ratio as the angle of rotation for Ted's house, and then we need to find out where Suzette's house is. So we're looking at Ted's house here, and we're talking about angle of rotation around the origin, and we're talking about Ted's house being in the second quadrant. So tangent here is negative, right? Cosine, all, sine, tan. So tangent is negative here, which makes sense because tangent is adjacent over opposite, and the adjacent is clearly a negative value. It's -6, and the opposite is positive 2.5. Okay. Well, if tangent is negative here, we need to find the other quadrant where tangent is negative. Well, tangent is negative wherever one of cosine and sine are positive and one of them is negative. Okay, so it's going to be out here in quadrant 4. Because in quadrant 4, cosine is positive, sine is negative, and negative over a positive is negative. Okay, so we're looking at this. Let's name this angle theta. Basically, we just need to know that Suzette's house has the same tangent ratio. It's in the 4th quadrant, and if it's in the 4th quadrant, where we're looking at now +6, -2.5, Okay, that's the answer. It's in the fourth quadrant, and we can put a little note there. I'll change my marker because that one's wearing out. If Suzanne has the same tangent ratio, comma, she is in Q4 at 6, negative 2.5. B. B says find the angles in standard position if the lines drawn from City Hall to each of the two houses are terminal arms. Round your answers to the nearest degree. So now we're looking at, we have an initial arm here, and we have one terminal arm going to Ted's house. So we're finding this angle, and we have one terminal arm going to Suzanne's house. Just draw a whole nother one, going all the way around to Suzanne's house, hitting at 6 and negative 2.5. Okay? So here we go. Ted's house is at a reflection of 6 and 2.5. Okay, so Ted's house, if we reflected it and looked at its reference angle, then he would be at 6, 2.5 over here. Okay? That's his reflection. Suzette's house is also a reflection of 6.25, but in the y-axis, so flipping over the x-axis, okay? The reference angle associated with these points is theta. So let's call this theta. And what do we know about theta? We know that the tangent of theta, let's put some notes here. So Ted is a reflection of 6, 2.5 in the y-axis. Suzette is a reflection of 6, 2.5 in the x-axis. And we've named this reference angle angle theta. And we know the tangent of angle theta because we know the two coordinates. We know x and y. Tangent is y over x, which is going to be 2.5 over 6. You can put that in your calculator. Take the inverse tangent of both sides. So the inverse tangent of 2.5 over 6. Should try it in your calculator. See if you get the right answer. If you don't, then you need to try it again. So the reference angle here is 23 degrees. And then we go back to the notes that we took last time. And so for Ted's house, where is he? Well, he's working with quadrant 1 and quadrant 2. So when we're dealing with that, then we've got he's at 180 minus theta. 180 minus our reference angle. So from the initial arm, you have to rotate through an angle of 157 degrees to get to Ted's house. And Suzanne, we can see she is 360 minus theta. So 360 minus 23. So to rotate from the initial arm around the circle to Suzette's house, not Suzanne, we're going to rotate through an angle of 337 degrees. Example 4 is our easiest of the day. Basically, we need 3 positive angles that all have the exact same terminal arm as 30 degrees. So I went ahead and drew one circle, one angle, in which the terminal arm rotates through an angle of 30 degrees. Okay? Well, how do we get another angle with the exact same terminal arm? We've already rotated through 30. Well, what do we do to that 30? We have to add 360 to it. Okay? So all we need to do is go from here, 360 degrees, and then 30 more. We end up with 390 degrees. Well, how do we get another one? Well, we just have to go around the circle once for 360, twice for 720, and then add another 30, and we end up being at an angle of 750 degrees. Well, what about another one? We'll go around the circle once for 360, twice for 720, another time for 1080, add our extra 30 that we started with, and we end up at 1110 or 1110. So there's three positive angles with the exact same terminal arm as a 30-degree arm. That's the only way to do it in B. And we can write down what we did here. All we did was this guy was 30 degrees. This is 30 degrees plus 360 degrees. This is 30 degrees plus 2 times 360 degrees. And this one was 30 degrees plus 3 times 360 degrees. Now down below, we're asked the exact same question, but this time we want 3 negative angles. Okay, so I'm going to go ahead and whip up our 4 circles again. Doesn't matter if they're not pretty. Our first angle rotates through 30 degrees, and now we need negative angles. So instead of going counterclockwise like we did up here for positive angles, we're just going to go backwards. And we're going to go backwards from our initial arm to the 30-degree arm, which is, and maybe I should just do it the same way we did it. We'll start with our positive 30 there, and then what will we do? We'll go backwards to that 30-degree arm, which is really just going to give us the original 30 that we had minus 360. So whether you go backwards or forwards, 360 degrees, you're going to end up at the exact same place. 30 take away 360 is negative 330 degrees. So we can put that in there. This is an angle of negative 330. Well, how do we get there again? Instead of going backwards just to there, we're going to go all the way around 360, and then another 330. So we did 360, 360, and then backwards 30. And same thing here. We're going to draw it out, and this time we're going to go backwards 360, 720, 1080, but then back forward the amount of 30, and we'll just double check what those are. This one is going to be 30 degrees minus 2 times 360 degrees. You can check that in your calculator. You should end up with negative 690 degrees. And this guy, we started at 30 degrees, and then we took away 3 rotations of 360 degrees. Check that in your calculator, you should end up with negative 1050 degrees. Those angles, all 8 of the angles drawn, or I guess 7 different angles, all have the exact same terminal arm, 3 extra positives here, 3 extra negatives here. All we did was rotate forward, counterclockwise, 360, 720, 1080, and then here we rotated backwards, clockwise, 360, 720, 1080. Okay? Practice problems for this lesson are from page 237 numbers 1 through 11.